Okay, so it's a pleasure to present Anne. Anne is a member of the RAVET, our external project collaboration, and also a member of the Miles library, or Miles models and everything. And she's visiting us this week with his student, who's sitting around, and he's going to stay for 3 weeks here too. And she made the PhD in Sussex University. Afterwards, she's been a senior postdoc. And then she became a lecturer in Preston. And she's there since a while. A number of PhD, supervised PhD, like Adam and some others. She is working on early-type galaxies, stellar populations, chemical evolution, interstellar medium, dust, radio properties, and so she's also multi-wavelength as well. Like, for example, ALMA, she told me that she got awarded with ALMA data recently. And well, she's going to talk today on the dust, properties of dust in early-type galaxies. So let's see what we can, with some surprises, I guess. So let's see. Okay, so.
Okay, thank you. Can you all hear me? Yeah. So it's a pleasure to be here at the IAC again. I'm going to try and tell you the story that we've uncovered about dust in early-type galaxies. We've attempted to get a census of the dust in certain patches of sky for galaxies in the local universe. So by way of introduction, I'll mention some aspects of galaxy morphology, and then I'll go on to introduce the Herschel Space Telescope, and then tell you about the results that we've obtained for early-type galaxies from this and other ground-based surveys, with the surprises that we found from that. I'll show you the trends that we found, including comparison with what's happening in the Virgo cluster, which is a really important hunting ground for trying to understand galaxies. We'll make the comparison with the Virgo cluster, and I'll summarize that and tell you what's coming up next in this area as well. So this is largely based on work I did with my last PhD student, Nicola Ajus, who was at UCLan with me. And we were working closely with various members of the GAMA consortium and the Herschel-ATLAS consortium, and a third consortium, which is those that observe the Virgo cluster galaxies, called HEVIX. So this is just showing a random cluster of galaxies, just to illustrate the different galaxy structures. This particular one also highlights effects of gravitational lensing, which I'll come back to later on a bit. But you can see spiral galaxy structures, smooth early-type galaxies, giant galaxies, etc. in here. And one of the main drivers for trying to look at multi-waveband observations of these galaxies is how did the shapes arise in the local universe. Regarding dust, this just shows two extreme cases, a face-on nearby spiral galaxy, well-known one, M51, where you can see the dust in absorption against the backdrop of optical light, plenty of dust following the spiral structure. That's on the left-hand side. And then on the right-hand side, you can see an early-type galaxy, a lenticular galaxy, which is a famous one in the Virgo cluster. And this one has a small dusty disk in its centre, about a kiloparsec across. And this one is interesting for this project because it turns out to be the dustiest giant early-type galaxy in the Virgo cluster. So the right-hand side is as dusty as it gets in Virgo. There's been lots of anecdotal evidence about the presence of dust in early-type galaxies, small amounts, and sometimes it's linked with observations of molecular gas as well. And this is an example where you can see HST observation, so we're seeing the dust in the centre of the galaxy in absorption, and you can see a fairly irregular structure in the centre, and at the top right is the molecular gas distribution following that. So the conventional picture of early-type galaxies was for a long time that they're cold gas and dust free. We've seen that there's anecdotal evidence for some early-type galaxies having dust and cold gas in to some extent. Another extreme example is shown here, well-known one. Centaurus A on the right-hand side shows a warped dust lane in an early-type galaxy. You see again that in absorption you can see the dust lane. On the left-hand side is some early results showing how the molecular gas and the dust emission are related. So you can see early and late-type galaxies plotted there. The filled symbols are the late-type galaxies, and you can see that they follow a trend that the molecular gas and the dust seem to be linked. But for the early-type galaxies, it's less obvious that there's a strong link between molecular gas and dust. But you can see in general there's less of it. That just shows other wave bands for Cen A, including the radio waveband emission in light blue and the X-rays in this galaxy in dark blue. And early-type galaxies are often associated with hot halos of gas which are seen in X-ray emissions, about 10 to the 6 to 10 to the 7 degrees Kelvin. And that and the presence of dust are a bit anomalous because you would expect in such a hot plasma environment that the dust would be sputtered in a relatively short time scale, so we don't really expect the dust to survive in those environments. And yet we see it in some cases. Here's some examples of early-type galaxies where we see dust lanes, which people have interpreted as coming from minor mergers. So we can see some examples here, and the reason that they think it's an external event, bringing the dust into the system, is because the dust is not generally aligned with the optical light. So when you see these misalignments, you wouldn't expect that if the dust was coming from stars within the galaxy itself, where you would expect it to follow one of the principal axes quite quickly. So in the morphology of both gas and dust, molecular gas and dust, we see these misalignments in early-type galaxies in some cases. This is from results from Davies et al. Last year. And also in the kinematics, we see misalignments of how the molecular gas is moving relative to the stars. So these are hints for an external origin for these cool gaseous phases in early-type galaxies. I want to just introduce a couple of well-known results in the literature over recent years, just to set the scene for galaxy evolution. One is, this one shown on the left-hand side, illustrates the effect of the morphology density relation for galaxies and how that's evolved over time. So the lowest plots on this diagram, for example, the red points show the distant universe, how the fraction of early-type galaxies behaved as a function of environment density. And you can see it's fairly flat. But if we come through to the nearby universe, the purple line, you see that early-type galaxies mostly cluster in dense environments. So that's a well-known result that has been published many times in many different guises, that early-type galaxies dominate in dense environments in the universe today. Another major result that we have peppered throughout the literature in recent papers is the effect of downsizing. And this is one I've shown for galaxies in general, irrespective of the morphological type, where you see that there was more specific star formation rate, higher specific star formation rates in the past, but in the local universe you see that these are segregated by morphological type as well, in terms of the segregated by the mass of the galaxy. So you can see on the right-hand side, the red curve is the most massive galaxies, and they show the least specific star formation rate. And the low-mass galaxies shown in blue show the highest specific star formation rate in the more nearby universe in this plot. So the action for star formation is going on in lower-mass galaxies now more than in giant galaxies. And that's true for galaxies as a whole. So low-mass galaxies have higher specific star formation rate today. So we have these observational bits of evidence about how the universe is behaving. And this is a particular example of downsizing. This is one particular early-type galaxy that we looked at in detail with the SALT telescope. And you can see from the spectrum it's got strong emission lines indicative of recent star formation. And you can see the absorption lines in the spectrum as well at the same time, indicative of older stars. So this is an example where you've got extended star formation going on to recent times, and we see the evidence in the spectrum for that. When we get rid of the emission lines and just look at the absorption line strengths, we can measure the typical characteristic luminosity weighted parameters for those, and we find that it's a very metal poor galaxy with old stars. So evidence for young and old stars in this system. The image shown there shows it's a smooth early type galaxy. This galaxy is interesting because it's in the Sculptor group, so it's fairly nearby, and we're trying to investigate at the moment this with integrated light data, but in future it may be a source where we can start to resolve the individual stars, and from resolved star data you can get much more information about what the star formation history is doing. So we may be able to see this in more detail with the large telescopes coming up on the horizon. So it's in the Sculptor group, which is fairly nearby. So it's an example of downsizing because we have star formation rate going on now in an early type galaxy. So we know from observations that there are transformations of galaxies. Just to show a couple of examples, here's one where you've got two late type galaxies, disk galaxies, interacting, well-known interacting pair. And here's an example of one at a later stage of a merger event, where you can see in the center, if you look at the surface brightness profile, it looks more like an early type galaxy, but you can see the relics of what happened in the past in the outer regions of the galaxy, and in particular you can see two strong tidal features indicative of kinematically cold material that went into making up that galaxy. So we see these dramatic events in the local universe. We also know from simulations that mergers of disk galaxies can make early type galaxies. And we know also from observations and simulations that minor events can have a wide range of influence on the morphology of systems. So things like the bloating of a disk, or quenching, or the growth of the halo of a galaxy can be affected by minor mergers and bits and pieces. So when these interactions and mergers happen, we're interested also in what happens with the gas and the dust. Is there any relic left over of what went on when you look at the dust later on in these systems, for example? So to look at dust, we used the Herschel Space Telescope, and I've shown you anecdotal evidence of dust in early-type galaxies. What we wanted to do was to find out how much is really in early-type galaxies en masse, an ensemble of galaxies. So we wanted to look at a complete sample. Herschel Space Telescope was in orbit from 2009 to 2013. It had a 3.5 meter mirror and 3 instruments on board, and we used the data from 2 of them to get flux densities in 5 different wave bands in the submillimeter. And here's a little plot of a dust grain. So this is the sort of thing we're investigating. Of course, we don't see that. We just see the integrated light from the dust itself. But it's heavy elements conglomerated together. So the survey we're a part of is the Herschel Astrophysical Terahertz Large Area Survey. It was a major key project for Herschel and took up about 600 hours of observing time and covered about 550 degrees square on the sky. And there were about 6 major science themes that were addressed with this one data set, one of which was to get a census of dust in the different types of galaxies in the local universe. This survey was designed to be in parallel with the GAMA survey, which had observed in specific regions of the sky, so Herschel was observing the same regions, and in particular, the GAMA survey had looked at 3 equatorial regions at 9 hours, 12 hours, and roughly 15 hours in the sky, so 3 little patches of sky. Looking at different regions is to try and overcome cosmic variance, and they had 2 other regions which I won't talk about here because we didn't have the data available at the time. We had the data available for the equatorial regions and all the associated data that went with that. So in matching the equatorial regions, there were at the time about 10,000 galaxies matched between Herschel and GAMA. So we observed these in the 5 bands, got flux densities in the 5 bands where we could. You can see here that the spatial resolution from Herschel is very, very poor compared with optical observations. So what we're getting is just the overall flux in each band from the galaxy. We have no imaging with the Herschel for these external galaxies. GAMA is a survey called the Galaxy and Mass Assembly Survey. It's a multi-waveband survey, including everything from ultraviolet from the GALAX satellite through to optical, near-infrared, and the WISE data cover the same area in the infrared, and then the Herschel data in the submillimeter cover the same area. So we have a broad spectrum of flux densities in different wavebands with aperture matching to get the same data from each galaxy. In future, there'll also be H1 observations of these galaxies as well with ASCAP. So it's a multi-wavelength survey led by Simon Driver, and you can see updates of that in 2011, 2016 published. It consisted of about 400,000 redshifts taken at the Anglo-Australian telescope based on input from the Sloan Digital Sky Survey imaging. So it went about 2 magnitudes deeper than Sloan in terms of the redshifts. And there's additional photometry from all these other wavebands that I've mentioned. So this is one example of the multi-waveband data we've got from one galaxy, NGC 891. You can see here from ultraviolet through to the submillimeter, and the observations and how it changes the appearance of the image. And I thought I'd show you a small patch of the area. This is roughly a square region in the R band, so optical SDSS image, showing a source in the center which we know is a submillimeter detected source. So this then shows the Herschel 250 micron image of that same patch of sky. So you can see in the center the source that's detected, but you see that the point spread function is greater than in the previous case, and you also see that the pattern is very different from what we saw in the previous image. So putting those side by side, we see a very different part of impression of the sky in these two different wave bands. So the left is mostly starlight that we're looking at, and of course the right is mostly dust. Some other stuff as well, but mostly that's where the dust is in the universe. So the central image you can see is detected. Other things do match up, but with very different patterns, very different levels than seen in the optical data. In the submillimeter, we have a number of different confusion events that we need to take into account. One thing is, which can be seen as a bonus for those looking at high redshift, but is just a nuisance for those trying to look at low redshift, is the negative K corrections, which bring the flux closer to the peak of a blackbody distribution into your observed band. So if you're looking at 100 microns with Herschel PAX instrument, and you look at high redshift, then it brings that flux into the band more, so you get more for your money in the distant universe. So in the submillimeter, you can think of the distant universe as being more lit up than you expect, especially if you're just used to optical astronomy, where you expect the 1/r² law to be in place. So that means we've got more confusion to play with. So we need to be more careful about matching our submillimeter sources to the other wave bands to identify the galaxies that are involved. Also, we have gravitational lensing in the submillimeter. So again, this can lead to confusion when we're seeing lens sources rather than real associations with the galaxy. So both of those things we've tried to account for, in particular the gravitational lensing, by a variety of different mechanisms which take into account how lenses would look in various submillimeter color plots. So it's a statistical result, but we've taken those out of the sample to try and clean it up of gravitational lens contaminants. So we sampled the three equatorial regions in GAMA and Herschel-ATLAS, and we looked at early-type galaxies, and we were able to do this because they'd been classified previously by members of the GAMA consortium. Lee Kelvin in 2014 had produced a catalogue out to a redshift of 0.06 in the GAMA regions for all the different Hubble types. So that's where we selected our early-type galaxies from. We then also looked through all those galaxies to look for obvious spiral features and throw out those small number of cases that had got through where you could clearly see spiral structure to just try to clean up the sample even more. We removed particularly flat galaxies because we don't expect ellipticals to be flatter than E7. And we removed small galaxies where we weren't confident with their morphological classifications. That left us with 771 galaxies, complete down to an R-band apparent magnitude of minus 17.4. So to set that in context, it's approximately the magnitude of the Small Magellanic Clouds, or thereabouts. So we're getting everything down to that magnitude level. And from the submillimeter data, we were able to investigate the dust temperatures and the dust masses of these galaxies. From the gamma data, we also had information about the stellar mass of the galaxy, the star formation in the galaxy from the ultraviolet emission, and also from optical colors and H-alpha emission. We had the types, the Hubble types, and we also had information about the environment. So another strand of the gamma community had characterized numerically the environment of all these galaxies using the nth nearest neighbor method. So from all this, what did we find? I'll just show you the AGN plot first of all to show how we removed AGN. This is a standard BPT diagram with optical line flux ratios where you can see a difference between where starburst galaxies lie and where AGN lie. All the grey points are all the gamma data in these equatorial regions, and the coloured points are the ones with the morphological classification in the nearby universe. So you can see most of them are late type SD galaxies in this swathe of star forming. The yellow ones in the star forming region of the plot. But there are a few, yeah. Yeah, so the two curves represent where the starbursts and the AGN are distinguished. So it depends in a nonlinear way on the two axes. Yeah, so one's from Kaufman, and the other one is the theoretical one from Cooley. So you see this in many plots of this type. And we used everything above we conservatively removed everything we thought could be an AGN above the solid line. So just keeping in everything that we were confident wasn't an AGN. So that's removing AGN if you can see emission lines in the optical spectrum. You can remove those. So the early type galaxies, you can see there's a few that were removed in that way. This gives you an idea of the imaging we were working with at the distances out to 0.06 in redshift. So you can see in the top panel 3 elliptical galaxies, and the lower panel has 3 lenticular galaxies. This is from SDSS imaging at the time. And the right-hand panel shows the histogram of detections. This is at 250 microns, so we counted it as a detection if it was above 5 sigma in 250 micron band. So hence there's a sharp cut-off there. So what did we find? We found 220 of the 771 galaxies were detected at 250 microns. So we called this sample sub-S. And the rest of the galaxies which weren't detected in the submillimeter at that level, we called the opt-S sample, and that contained 551 early type galaxies. So already we're detecting quite a large proportion of the galaxies in the submillimeter, which was a bit unexpected. This shows one of the galaxies that was detected in 3 of the Herschel bands and in the optical band. You can see the galaxy is nicely resolved in the optical band, but the point spread function doesn't allow you to see any physical structure in the Herschel bands. So it's just an overall flux that we're getting, aperture match to the red band. So from these fluxes, we could put the 5 fluxes together and measure temperatures by fitting modified black body curves, as the top equation shows. And so we get a best fit overall single temperature from that. And then we could put that into the lower equation, which estimates the dust mass. And this relies on knowing the absorption coefficient, which we took from Dunn et al. In 2011. That is quite uncertain, but we did the same for all the galaxies. And if we put the temperature in there, the dust mass is very sensitive to the temperature. And so you could estimate what the temperature was. K is the K correction, D is the luminosity distance in that equation, and the F is the flux density at 250 microns. So we got dust masses and temperatures for the 220 detected galaxies or thereabouts, if we had more than one submillimeter band available to fit the curves to. This is a plot of specific dust mass, So dust mass to stellar mass ratio on the vertical axis, plotted against the UV minus optical colour on the horizontal axis, which is a measure of the star formation rate. In the colour quantity, you can see the different masses of the galaxies. So we've got blue and green are low mass galaxies, red and yellow are the higher mass galaxies. So we can see trends here between the specific dust mass, the UV to optical colour, and the stellar mass in early type galaxies as a whole, for those that are dust detected. So in general, the smaller galaxies appear to be relatively dustier and have more star formation going on. So this is, again, very much like the downsizing that we see in populations of galaxies as a whole. So in early type galaxies, we're seeing the effects of downsizing as well. And this was published in 2013 in Ajus et al. In the monthly notices. We found a number of differences between these two samples. Another one that we found was that they're less centrally concentrated than the non-detected galaxies. And also they tend to have bluer colours than the non-detected galaxies, which you might expect if there's more star formation going on as well. So various different statistically significant differences between the samples. And here was another one showing the colour magnitude relation. So the detected galaxies are shown in blue, and the non-detected galaxies are shown in black. And you can see they lie in different parts of the colour magnitude diagram. The blue points, the dusty ones, tend to lie more in the green valley of this plot than the non-dusty ones. So the lines show where people think the green valley is defined in this diagram, and you see a lot of blue points in that region, much more than the black points. At low luminosities, there is a scatter of black points down as well, but by and large there's quite a strong segregation of points in this diagram, just based on whether they're detected or not in the submillimeter. The mass range of the two samples is not that different. We looked at environment density for the two samples and found that the detected ones tend to be in lower density environments compared with the non-detected ones. So the blue histogram shown there is for the sub-S sample, and you can see that they're in lower density environments. However, the GAMA survey, because it only covers certain regions of the sky, and we're looking in the nearby universe, is not so sensitive, doesn't have so much influence from clusters of galaxies. It's mostly sampling the field and groups of galaxies. So the overall extent of this horizontal axis doesn't get to the densest regions of the universe. There is a spread, but it doesn't go very dense. So we wanted to look at a region which is dense, which had Herschel data. So we went to the Virgo cluster survey, or Helix survey, where they have observed galaxies in general. And for a sample which was absolute magnitude limited in the same way as our Herschel sample, we found early type galaxies were detected in 33 out of 123 galaxies. So 33 non-detections and 33 detections rather, and 90 non-detections of early type galaxies. Of course, in the Virgo cluster you can classify things much more easily than you can in the gamma sample. So we had knowledge of whether it was an elliptical or a lenticular very clearly. But we put those together because in the gamma sample you can't tell the difference between those so well. So we just had an early type galaxy sample. So this is obviously a dense environment, but it's also much nearer than the gamma sample. So something like 17 to 23 megaparsecs away. We took the Herschel-ATLAS and the Helix sample and analyse them in the same way. So the Gamma and Virgo samples, we analyse them in the same way to try to make a comparison as like for like as possible. So in order to do this, we used spectral energy distribution fitting. This diagram just illustrates the importance of the Virgo cluster to us as a whole. You can see on here, I use this, we're in the local group, and here's the sculptor group that I mentioned earlier where NGC 59 is, so it's quite close. And then there's a few other clusters around the place, but this is the Virgo cluster. In the schematic diagram, it illustrates the dominance of the Virgo cluster, and therefore how tempting it is to use that as a hunting ground for understanding galaxies in general. So there's a few thousand galaxies in the Virgo cluster, and well resolved. This is one of the fits to one of the Virgo cluster early type galaxies, so spectral energy distribution fitting, and we've got a number of flux density points shown in black, and you can see, for example, galax data, optical and infrared data, WISE data points, and the Herschel data points. So all for the same total galaxy region, and all flux densities, so we can fit energy balance models to these points. And the one that we fitted, there's many different ones around, but the one we used was MAGPHYS. And what this does is takes account of contributions across multiple wave bands in modelling what's going on in the spectral energy distribution. So it's including the starlight and the dust. So the red line includes the dust, and the blue line shows what would happen if you took the dust away, what the model spectral energy distribution would look like. So you can see, for example, the ultraviolet gets redistributed into the infrared when you've got dust in the galaxy. The 5 points on the right-hand side, you can see the modified black body nature of those points, and that gives you the temperature of the dust. So from MAGPHYS fits, you can get a wide range of parameters, including information about the current star formation rate, the stellar mass of the system, and the old and young star contributions, information about the extinction, and the dust mass and dust temperature, and even split it into different components of the dust and have a warm dust component that you can get characteristics for. So there are a wide range of parameters, some of which are better constrained than others. For example, the stellar mass is very well constrained by these methods. We also had, in addition to that, the environmental density, which we had recomputed in exactly the same way for the Herschel data, the gamma data rather, as for the Virgo cluster data. So we had used all the stars, all the galaxies in the down to a given absolute magnitude level to get local density parameter for each galaxy. In these SED fits, there is some uncertainty about what the UV is doing, especially when you've got low levels of star formation rate, because there's contributions from evolved stars, and we don't know those particularly well in the ultraviolet. We know it's a contribution, and if you've got any level of star formation, it often wipes out that contribution, which is low level. But if you've got a very low level of star formation, then you become uncertain about whether what you're seeing in the ultraviolet is telling you about the star formation rate or is just telling you about the evolved star contributions. And I understand there's people working here on that part of the spectrum to distinguish between different possibilities. So comparing the Gamma and Virgo cluster data, on the left-hand side, we see the submillimeter detected samples in each case, and we can see clearly the different environmental densities measured on a like-by-like case, as you'd expect. So the Virgo cluster occupies a denser region. So we wanted to look to see if that's true for the Gamma and Virgo samples as a whole, irrespective of whether they're detected in submillimeter or not. And that's shown on the right-hand side. And when you put all the galaxies into the mix, all the early-type galaxies, you do see some overlap, but there's a sharp drop-off. And so there isn't much in the way of sampling of dense regions of the universe in the Gamma survey. So we're sampling very different densities. What about the dust masses? I've given you the number of detections, but here's the actual dust mass normalized by the stellar mass plotted against stellar mass. So this is quite a busy diagram, but you can see in blue the submillimeter detected Virgo early type galaxies, and in red the submillimeter detected gamma galaxies. The error bars are indicated here, and they're not, despite the fact that Virgo's a lot closer, they're not so dissimilar, the error bars. They were going down to similar sort of flux levels. The lines, for instance, these two blue dot dash lines, represent where the limits of detectability for the Virgo cluster galaxies are. So below the lowest blue line, we don't expect to detect any Virgo cluster galaxies. And this swathe is a region where we expect to partially detect them, depending on where exactly they are in distance and what exactly the spectral shape is. Above the upper blue line, we expect to detect everything that's sitting there in Virgo cluster. So that's quite a narrow swathe for Virgo cluster because it's not a very deep distance range. But for Gamma, it's a wide distance range, so we have a much broader swathe of partial detections. So between the two red lines is where we expect to increasingly detect systems, and then above the solid line, the dashed line at the top there, we should expect to detect anything that existed above there, 100%. So there's some interpretation to be done of this diagram because of the flux limits and the different distances involved. But what you can see, irrespective of that, is that there are no blue points sitting high and to the right in this diagram. So there are no really dusty early type galaxies in the Virgo cluster. Whereas in the Gamma sample, we've got quite a large selection of things going on there. So lots of dusty galaxies, a bit unexpected. We didn't really expect to detect so many early type systems. You can see it in the range of the dust masses from the two samples. The Virgo cluster had dust detected masses ranging from 10 to the 4 to about 10 to the 7 solar masses, whereas the H-ATLAS sample, the range was about 10 to the 5.5 up to about 10 to the 8, the most extreme. So 10 to the 8 solar masses of dust in an early type galaxy is quite unexpected. We ran a number of tests on this diagram to try to understand, are we just seeing the different sample selection criteria here, and are these samples really underlying the same? And to do this, we did a one-step KS test, so a very coarse KS test, Kolmogorov-Smirnov test, by putting a line parallel to the limiting lines through the dustiest galaxy. And that's that one that I showed you earlier, which had a little dust layer in it. So that's where VCC 1535 sits in this diagram. That's the dustiest one in Virgo. And so above and below this line, we can work out what the numbers are of systems detected above the line and systems which lie below the line, including everything that's detected below the line and everything that's non-detected below the line as well. So we've got, in the case of the Gamma sample, 162 above the line versus 609 below the line. And by design, we've got in the Virgo sample 0 above the line and 123 below the line. And a KS test from that simple distribution gives a probability of less than 1.1% of being chosen from the same sample. We also ran Monte Carlo simulations to see how, if you took the Virgo cluster galaxies and peppered them out to the distance of the Gamma galaxies, how many of them would you detect? And it turns out to be, in a sample of 500 Monte Carlo runs, you would typically detect one galaxy, which is the one I've shown you there. So one compared with the 162 out of 771 that's shown there is a very low proportion. So they're very different samples. Despite the flux limits difference, we can see that they are very, very different samples. This was published in 2015 by Adjuce et al. In Month Notices. Another plot that we showed in that paper was the specific star formation rate plotted against stellar mass. And here again you can see the difference between what's going on in Gamma and what's going on in the Virgo cluster for these early type galaxies. So the blue points are again the Virgo cluster ones, and the red points the Gamma ones. So you can see they're showing the same qualitative trends, but with very different slopes, and they tend to converge to a similar region of the diagram at high stellar mass. The green points are showing cases where the interpretation of the UV light becomes ambiguous because you're getting down to very low levels of star formation rate. You can see from the histograms on the right-hand side that these are very different distributions. So, in summary, statistically we've found 29% of the Gamma galaxies were detected in sub-millimeter, and that's out to a distance of about 257 megaparsecs. And 27% of the Virgo cluster were detected, and that's out to a distance of about 17 to 23 megaparsecs. So that different distance, you wouldn't expect to be detecting the same proportions. You'd expect to detect much more in Virgo because they're so much nearer. The KS test shows that the distribution in this specific dust mass versus stellar mass diagram gives a less than 1% probability of those two samples being selected from the same distribution. And it's important to realize that Virgo may not be characteristic of what's going on in the wider universe, because from the Herschel data, there was a project called the Herschel Reference Survey, which tried to observe specific Hubble types and characterize them. And that survey for early types was dominated by the Virgo cluster. It did have galaxies in other regions of the universe, but a lot of the galaxies came from the Virgo cluster. So that has been used in the literature as characteristic of early type galaxies as a whole. What we're showing here is that that may not be the case, doesn't seem to be the case in the dust properties. So a Virgo cluster doesn't seem to be typical of the wider local universe in early type galaxies. This may be because of the environment density effect, or it may just be that the Virgo cluster is unusual. So to answer that question, we'd need to look at other clusters. And one other cluster we may be able to do this task on is the Coma cluster, because that had been observed with Herschel as well. But that's yet to be done. So it's an open question yet whether we're seeing a real environment effect or whether we're seeing just an unusual set of galaxies in Virgo compared with the rest of the universe. So coming back to those broad themes of galaxy evolution that I described earlier, we see transformations of galaxies, major and minor events. From the stellar population analysis, we also know that massive early type galaxies tend to be the oldest galaxies, so the conventional red and dead galaxy picture, and that they occur in clusters of galaxies primarily. From the work we've done here, we've seen that lower mass early type galaxies have more dust and star formation in them, and that the dusty early type galaxies appear to be in lower density of environments than the non-dusty early type galaxies. So putting all this together, it's consistent with a picture of the end stages of galaxy evolution being massive ellipticals, and everything is still tending towards that. It's tended towards that in a rapid way in clusters of galaxies, but less rapidly in the field and in groups. Plus there may also be some reaccretions of gas, so some rejuvenation from that one-directional picture of galaxy evolution. In future, what we want to do with investigating the dust in galaxies is, the next question is to ask, can we find any more dust in these galaxies? And dust could be easily hidden because as you decrease the temperature, the flux drops very rapidly for the emission from dust. So it's potentially possible that we have lots of hidden, very cold dust in these systems. And if that's present, then that tends to scupper the interpretations of minor mergers, because you then have too much material for it to have come from a minor merger event. So that's yet to be looked into, and the way that we're going to look into that is to use the SCUBA 2 instrument on the JCNT to look at longer wavelengths. And we have plans in place for doing that now. The other direction that we want to go in is to actually see what's happening to the configurations of dust in some of these gamma galaxies. So to do that, we've applied for ALMA time to look at some of the dustiest cases and see how their dust distributions look, to see if they're aligned with the galaxies, to see if they're regular or irregular distributions. If they're regularly distributed in a disk, what we can do is to use radiative transfer modelling to try to assess if the stellar radiation field is responsible for steady heating of that dust. So with experts at UCLAN on radiative transfer analysis, that's what the data can be used for. So to give an idea of some of their models, including radiative transfer models, collisional heating models, we can use their predictions for spectral energy distributions. Here's an example, another anecdotal example of dust in a nearby early-type galaxy. But this one is too near and too large to observe with ALMA, unfortunately. But what we do see here is a hint that there's not a disk structure, but there may be rings of dust. So we might find that when we get data back from ALMA, we're seeing rings of dust rather than dust disks, which would be interesting in itself. So this particular one is not being requested for ALMA time, but others are, to see what's happening in early-type galaxies as a whole. And we have data for 4 galaxies hopefully coming soon. So in summary, we've looked at GAMA and Herschel Space Telescope datasets for early-type galaxies in the nearby universe, and found lots of dusty early-type galaxies, which was highly unexpected, with star formation going on, and this tends to counter the conventional view that they're dust-free and cool gas-free. We found that lower mass galaxies are more affected. In other words, we're seeing downsizing in early-type galaxies, and that they tend to be in rarer environments compared with the non-detected galaxies. We find the Virgo cluster looks different from the gamma sample in that we're detecting very few dusty early-type galaxies in the Virgo cluster. And just to remind that we're not including all the dwarf galaxies in this analysis. There are some dusty early-type galaxies in the Virgo cluster in the dwarf category, but it's not in this comparison because we don't have those galaxies in the gamma sample to observe. So Virgo cluster doesn't look to be very representative of what's going on in the wider universe. So is this an environmental effect in general? With future work we have to answer that, and we can look to see if there's yet more cold dust which would affect the interpretation of where the dust is coming from in these systems, and to model the dust distribution with radiative transfer. And thank you for listening, and if you want to ask any questions, you're welcome to do so.
questions, a few.
The question that I would like to ask is it possible that some of the gamma galaxies are misclassified, spiral, faint, low-mass spiral galaxies? I think that
It's a very good question, and we have pondered long and hard and worked hard to try to answer that. And the answer that we came up with is there may be a small fraction which are contaminants still, but it's not going to change the story. If say 10% of those high dusty galaxies turn out to be late types, it's not going to change that picture dramatically. There'll still be a lot of early types. And the other thing to say about that is we have higher resolution data coming from the kids survey from the VST, which will help us to address that issue more specifically. So we've got it's higher spatial resolution than the SDSS images. Thanks.
Yeah, I have many questions, but I would concentrate on the most massive galaxies, those with the masses above 10 to the 11 solar masses. I mean, that figure is fantastic for that. So if you trust this, the amount of dust is of the order of 10 to the 5, 10 to the 6 solar masses in dust only. Okay? So, but if we understand correctly the formation of these objects, they form these 10 to 11 solar masses very early on, redshift 2, redshift 3, in a huge starburst with the star formation rates of the order of 1,000 solar masses a year.
Yeah, everything happening very fast.
So my question to you is, where all the dust that presumably was formed in this huge starburst is right now? Because, I mean, do you think the energy of the starburst was big enough for destroying the dust? Or is simply that the dust is now so cold that we cannot observe it?
Well, in those really energetic systems, those high luminosity early type galaxies, you often get X-ray halos. So it's that you don't expect the dust to survive in, because you expect sputtering to destroy any dust in a very short, relatively short time scale. There has been some simulations last year of one warped dust disk which seems to be able to be surviving for a gigayear or so. And there it was because it was being continuously fed from outside to maintain that warped dust disk. So they had a longer survival time. There may be issues to do with how the dust is configured in the galaxy, how it's protected from that harsh environment. But to my mind, that's the hardest thing to answer. If you've got X-ray emission, why is the dust still present? So I'm not sure if that addresses what you were asking, but you wouldn't expect it to be detectable in X-ray emitting massive early type galaxies. It's been produced, but it's been destroyed. So we expect it to be produced from red giant stars, and continuously so, but it's easily destroyed in sputtering.
So somehow the trend is natural then. So larger the most massive the galaxy is, potentially it was also stronger, the star formation rate, and also the destruction, the destruction of the dust was also higher. This is what you mean? Okay.
Interesting.
So following on the same kind of objects, for the Virgo guys, do you happen to know whether they're fast rotators, slow rotators?
No, that's an interesting question too. I think we should look at that, but it's not going to change the overall difference between the two samples.
No, but the origin of the two types is
we do have the elliptical versus lenticular, which obviously in the Virgo cluster we believe more than in the gamma sample. They were classified as elliptical and lenticular in the gamma sample as well, but I don't have any confidence that we can see the difference between those two at those larger distances. So it was a surprise to me that if you go out to less than 0.1 in redshift, classifying anything gets very, very hard beyond that, morphologically.
More questions?
I just wonder why we should expect a relationship between the stellar mass and the dust, thinking in the context of what you introduced at the beginning, that the idea in these early type galaxies, most of the dust might come from an interaction, a merger, environment. So if I think, for example, a nearby object like Centaurus, say, and this irregular dust morphology, well, it's a ring, or sombrero, or some others you have shown, well, we measure the amount of dust. Why should I expect in the general context where you don't see how the dust is distributed, a relationship?
Why should we expect the lower mass ones to be dustier? Is that the question?
Why should I expect mass of dust, mass of stellar be connected?
Well, my personal impression is that we're seeing downsizing, so we're seeing more going on in the low mass galaxies than in the high mass galaxies proportionally. That's how I interpret that. But without seeing the shapes across the masses, it's hard to address really what's happening with those systems.
Well, the point is because, as we know, in the near universe, it shows quite irregular morphology. It does not look like it's something mixed together with the stellar population, which I will think that most of the results you get is globally, I imply somehow, perhaps it's a naive way, that the dust stars are all together. But in the near universe, we see quite, external origin, as you say, because it's misaligned, not related at all. So I just was wondering why should I expect.
Yeah, and some of the samples, smaller samples in the past, have shown very little relation, but we find a very broad relation here. But do remember, in this diagram, we're not detecting fully everything to the lower left part of the diagram. So there may be an upper envelope, but it's not necessarily the full story that there's a relation going on there, if you see what I mean. So the lower left is where we're hitting the flux limit problems. So the full picture of where the galaxies are in this diagram, we can only see sort of the tip of the iceberg on the upper right.
We have time for one more short question. She's here all the week, so.
Yeah, did you try to for those, let's say, ellipticals, the ones that showing some dust, there's any link maybe, or did you try to check whether these galaxies show the ultraviolet upturn or not?
Yes, so that was in, I can find it. So it's not directly the ultraviolet upturn, but it's a specific star formation rate obtained from that ultraviolet light. So on the vertical axis, the specific star formation rate is plotted against mass. So this, I don't know if this fully answers your question, but we do see a very different picture between the Virgo and Herschel and Gamma samples there. So there is a link between what the dust is doing and what the star formation rate is doing in these systems, very broadly speaking. And that was in an early diagram as well. So there you can see the colour more directly, the NUV minus R, plotted against the dust. So we've got trends between the colour, the dust, and the stellar mass going on in that diagram. Yeah, to distinguish, yeah. Mm-hmm. So at the moment we've just been using the near ultraviolet as a better indicator of the star formation rate in this context.
Good, so I'm looking at the clock, and I think we should probably stop here. So let's thank Anne for the nice talk. And Anne is here the entire week. She's in the top floor of the first corridor, in one of the second door on the left, if you want to talk to her. Yeah. Thank you.